Previously, we described reality as an intricate dance between observer and observed, fundamentally shaped by limited resources. But what exactly happens at the limit of those resources? Tonight we're going deeper. If reality has constraints, then intelligence itself must have a speed limit. Welcome to episode 36 of SpaceTime Cafe. Enjoy the show.
Does intelligence have a speed limit? And if it does, what happens when you actually reach it? Tonight, we're going to explore a pretty mind-bending idea. That thought itself might have a fundamental speed limit, one dictated by the very geometry of information.
And not just a limit, but that meaning, like true understanding, only really emerges right there at that critical edge.
Exactly. So our mission today is to cut through the complexity. We want to give you a shortcut to understanding this really revolutionary concept. We'll show you how fields that seem totally unrelated actually come together.
Yeah, it's surprising how they converge to give this unified picture of intelligence.
We're pulling from a really diverse stack of sources for this deep dive.
You really are. It's everything from cutting-edge neuroscience studies, complex systems theory,
All the way back to foundational ideas in number theory, even quantum physics.
which sounds like a strange mix, I know.
It does. But what's so fascinating is how these fields, things you'd think have maybe nothing in common, they don't just touch. They actually, converge. They reveal this surprisingly unified view of intelligence and meaning.
That's the key. It's unified.
So you're going to get some, I think, truly surprising insights into how our brains work, maybe even how AI fundamentally operates.
And hopefully without getting too bogged down in the super dense academic details, we're trying to distill the core nuggets here.
Okay, so let's start unpacking this. We've seen just incredible advancements in AI recently.
Oh, absolutely. Faster models, huge neural networks.
Billions of parameters that can generate text, images, even whole virtual worlds. It's staggering.
It really is. Yet despite all that raw power, that scale, we still grapple with defining what intelligent truly means.
Yeah, and more importantly, how do we reliably get there? How do we achieve it?
That struggle often shows up in these really fundamental challenges. Generalization.
Explain that a bit more.
Current AI models are amazing at the specific tasks they were trained on, right? But ask them to take that learning and apply it to something totally new, something outside their training data.
And they often stumble.
Exactly. They might miss the subtle context of a new problem, or they struggle to adapt if the environment changes.
So they're fast, incredibly fast at processing, but maybe lack that deeper comprehension, that understanding.
Precisely. That flexible, robust intelligence seems harder to pin down.
And this challenge, deep down, it often comes back to this classic tension in machine learning, doesn't it?
The old trade-off.
Yeah, between variance and bias.
So variance, think of it as like undirected entropy, randomness, chaos.
Like unshaped clay.
That's a good way to put it. A model with high variance is just too sensitive. It overfits.
Meaning it learns the noise, not the signal.
Exactly. It basically memorizes individual data points, quirks and all, instead of the deeper underlying patterns.
So it's too flexible, too easily swayed by tiny details.
Yeah, like trying to predict global climate by just looking at yesterday's temperature in your backyard.
Got it. Too specific, too brittle, easily confused.
And then you have bias on the other side.
The opposite problem.
Right. Bias represents information that's already compressed, maybe too structured, often pretty rigid.
So these models underfit.
Correct. They're too simplistic. They ignore crucial complexity in the data.
Like predicting a car's performance based only on its color.
Perfect example. It ignores the engine, the aerodynamics, everything important. It's just too rigid in its assumptions, can't adapt to richer realities.
Okay, so the traditional approach, which in the textbooks, it's always been about finding that sweet spot, balancing variance and bias to minimize the total error.
The balancing act, it's viewed as this purely statistical optimization problem.
You dial down variance, maybe counter bias by adding complexity, like a teeter-totter you're trying to keep level.
Constantly tweaking, always compromising a bit on both sides.
What if it's not just a statistical game?
What if it's something deeper, more
Deep,
fundamental,
really.
almost physical?
That's the shift in perspective we're exploring today.
Exactly. We want to invite you, the listener, to think about this differently, to explore a more fundamental truth about how knowledge is acquired, how it's processed.
Something tied to the very spectral properties of how information moves.
Seeing learning not just as curve-fitting, but as this dynamic process rooted in the geometry of networks.
Okay, so to really get this shift, let's look at the brain itself.
Right. Imagine the brain, or even a large artificial neural network, as this huge, complex communication graph.
Information flowing across billions of connections, neurons firing, units processing.
It's an incredibly intricate web. What's amazing is how efficient this biological network actually is. Studies on connectome topology, that's just a fancy term for how the brain's wired up,
Okay.
they consistently show the brain doesn't just grow randomly. It evolves towards being sparse, but highly efficient. We see architectures described as small world and high expansion.
What does that mean practically?
It means your brain connects distant regions with minimal wiring, keeping the cost down. But it maximizes how fast and reliably information can spread.
Like designing that efficient city you mentioned.
Yeah.
Fewest roads, but quick travel.
Exactly. The brain seems to naturally optimize its architecture for incredibly efficient thinking. It allows for this fast, distributed communication.
And you actually see evidence of this during peak performance.
Yes. When you're in that flow state, deep focus, or you have that sudden aha moment,
Yeah.
brain scans actually show an increase in what's called spectral synchrony in the relevant brain subnetworks.
So more coherence, faster signals.
More coherence, faster propagation, and importantly, no signs of overfitting. It's like the brain hits this perfect operational state. It's beautifully optimized.
Wow. Okay, so this optimized flow, this leads us somewhere specific, doesn't it?
It leads us directly to a really crucial concept, the spectral gap.
All right, let's break that down.
Imagine you have this network, like the brain. You can represent its connections mathematically, right? Using matrices, adjacency matrices, Laplacian matrices.
Just tables of numbers showing who's connected to.
Pretty much. Now, the spectral gap is defined as the difference between the largest and the second largest eigenvalues of this matrix.
Okay, eigenvalues sounds a bit technical.
Don't worry too much about the math. Think of eigenvalues as fundamental measures of how quickly information can move or mix within that network, how well it distributes a signal.
So a bigger spectral gap means?
A bigger gap means the network is better at quickly integrating information, synchronizing activity across different parts.
Faster mixing, faster synchronization.
Exactly. It fundamentally governs how quickly signals propagate, how rapidly different regions can coordinate.
Can you give an analogy?
Sure. Think of a drumhead or a violin string. If the string is loose, small spectral gap, you get slow, mushy vibrations. The sound takes longer to spread, notes are indistinct,
Okay.
but tighten it up, increase its spectral gap, so to speak, and what happens?
You get a crisp, fast, clear tone.
Right. The vibrations propagate rapidly and coherently across the whole thing. That's what a large spectral gap gives you for information in a network. Speed, clarity, coherence.
Got it. Speed, clarity, coherence. Now let's shift gears slightly and talk about something maybe even more elusive, meaning itself. When we really understand something, or even when we compress data, like a JPEG image, or distilling a huge research paper down.
What actually stays the same? What's the irreducible core?
Yeah, what's that essence of knowledge that somehow persists through all the changes, all the compression?
This is a massive question, obviously. Philosophers, cognitive scientists, physicists have puzzled over it for ages.
But this framework we're exploring offers a pretty revolutionary answer, doesn't it? Drawing on physics.
A profound inspiration from one of the most elegant theorems ever, Emmy Noether's theorem.
Noether's theorem. Can you give us a quick refresher? It's beautiful, but maybe not familiar to everyone.
Absolutely, it's truly fundamental. In simple terms, Noether discovered that for every continuous symmetry in a physical system,
The symmetry meaning something stays the same even when you change something else.
exactly, if a system has a continuous symmetry, then there must exist a corresponding conserved quantity.
Like conservation of energy.
That's the classic example. If the laws of physics don't change over time, if they have time translation symmetry, then energy must be conserved.
And if they don't change based on location, spatial translation symmetry.
Then momentum is conserved. These conserved quantities, energy, momentum, electric charge, are often called Noether charges. They're the bedrock constants in our physical descriptions.
They persist no matter how the system transforms, as long as those underlying symmetries hold.
Correct. The symmetries are the deep, unchanging rules. The charges are what those rules protect.
Okay, so here's the leap, the big claim.
Here it is. Meaning is the Noether charge of cognition.
Wow. Say that again.
Meaning is the Noether charge of cognition.
So meaning is the thing, the irreducible essence that stays conserved, that persists no matter how you change the frame, the compression, the representation.
As long as the underlying symmetries of intelligence are respected.
Just like energy persists through physical changes, meaning persists through cognitive changes.
It's precisely how physics thinks about fundamental conserved quantities. And it's a level of formal clarity you don't often find in standard cognitive science or ML discussions.
How does this connect to how we think the brain actually works, like predictive coding?
Great question. It maps incredibly well. In models like predictive coding or active inference, the brain's job is basically to minimize surprise or free energy.
Trying to predict the world efficiently, given constraints like energy cost.
Right. That minimization of surprise, that's essentially the divergence term, the math cal and the framework we'll discuss. Now, think about different senses, sight, sound, touch, or different mental models, or even different contexts.
These are like different perspectives on the same reality.
Exactly. They're like different gauges, different ways of representing the same underlying world state.
Okay.
Yet, despite using these different gauges, your brain manages to arrive at stable, coherent conclusions about what's going on.
That stable conclusion. That's the meaning.
Yes. Let's try to sketch it out. Imagine an observer bundle framework. You've got a space that's the world, everything that could be.
Right.
Then you have an observation bundle. This carries all the different ways you can represent that world, your actual data encodings, your mental models, your raw sensory input.
Got it. World versus representations of the world.
Now, crucial here is the gauge group. These are transformations you can apply to your representations.
Like what?
Reparametrizing your data, maybe relabeling sensors, using different compression algorithms, things that change the description, but ideally preserve what's actually observable given certain costs or resources.
Okay, so transformations that shouldn't change the underlying truth, if done right.
Exactly. Now, our cognitive Lagrangian, let's call it mathicus, is a mathematical formula that balances several key forces.
Okay, what are they?
First, there's cost. This could be metabolic energy used by the brain, computation time, memory. Resources aren't free.
Makes sense.
Second, divergence. This is that mismatch or surprise between your observation or prediction and the actual state of the world. Minimizing this is like the brain minimizing free energy.
Got it. Cost and surprise.
Third, redundancy. This is a penalty for inefficient representations. Carrying more information than strictly necessary, spectral redundancy.
So be efficient.
Right. And then you have these trade-off parameters, Greek letters like beta and lambda, that act like knobs controlling the balance between cost, surprise, and redundancy.
Okay, so you're balancing these factors.
Yes. And here's the theorem, the Noether information theorem. If this whole cognitive Lagrangian math cult remains invariant unchanged under a certain class of these observer transformations, meaning it has a gauge symmetry, then there must exist conserved information quantities.
And those are the meaning charges?
Those are the meaning charges. Formally, meaning becomes the bits that persist when we change sensors, encodings, or mental frames operating at a fixed budget of cognitive resources.
It's what survives compression.
Precisely. It's the invariant information.
Wow. Okay. But what happens when meaning isn't conserved, when the symmetries break?
Now we get into curvature. Think of it as confusion or obstruction to understanding.
Curvature in cognitive space.
Imagine your understanding is flat, zero curvature. This means descriptions commute. If you describe something using path A, then path B, you end up at the same conclusion as doing B, then A.
Like simple math. 2 plus 3 is the same as 3 plus 2.
Exactly. This corresponds to automatic, effortless processing. Daniel Kahneman's System 1 thought, procedural knowledge.
But curved understanding.
That's where things get interesting. Non-zero curvature means path-dependent inference. The order matters. This is effortful, reflective cognition, Kahneman's System 2, which taxes your prefrontal cortex.
Why curvature?
We use the concept of holonomy. Think about geometry. On a flat piece of paper, if you trace a path out and back following certain rules, like parallel transport, you end up exactly where you started, facing the same way.
Okay.
But try doing the same on a sphere. You trace a path, you might end up back at the start, but you might be facing a different direction. The path itself induced a change.
So the path mattered.
In cognition, if a concept doesn't close on itself after you've looped through different perspectives or transformations, you feel that dissonance, that confusion. Wait, these two ideas don't quite line up.
And that's why certain brain areas light up.
Plausibly, yes. The prefrontal cortex, PFC, and hippocampus are crucial for executive function, abstract rules, novelty, building models. They light up when we need to compute across these different gauges, trying to reconcile different representations and find that invariant meaning in a curved, complex space.
So they're navigating the curvature.
They're trying to. And when this curvature becomes pathological, think severe psychosis, hallucinations, it might signify a breakdown, a loss of that invariant structure, a failure to conserve meaning, cognitive instability.
That's a really powerful way to frame it. It makes you reconsider those aha moments again, doesn't it?
Absolutely. Were they moments when a conserved meaning just snapped into focus despite looking at it from different, maybe confusing angles?
How might defining meaning like this as a conserved quantity under cognitive transformations actually change how you approach learning or problem solving?
It suggests focusing on the underlying symmetries, the core invariance, rather than just surface features.
Okay, let's dive even deeper now. If meaning is conserved at this critical point, how does learning get us there? You said it's not just optimization,
Right. It's a phase transition.
like water freezing into ice.
Exactly, that kind of fundamental shift. Learning, whether in AI or biology, isn't just incrementally getting better. It's this process of condensation,
Condensing what?
condensing that high variance, the undirected entropy, the chaos, into structured bias.
Yeah.
Into meaningful, compressed information.
And this happens at that specific spectral bound we talked about.
At that critical point, yes. It's where the raw, disorganized stuff suddenly crystallizes into actual knowledge.
Then the mathematical connection here is, you said it was mind-blowing.
It really is. It goes back over 100 years. First, to the incredible Indian mathematician Srinivasa Ramanujan.
Right. His work on the partition function, Pn.
Pn counts how many ways you can write a whole number n as a sum of positive integers. Like P4 is 5, because 4 can be 4, 3 plus 1, 2 plus 2, 2 plus 1, or 1 plus 1. What Ramanujan discovered, along with Hardy later, was its unique growth rate. It doesn't grow polynomially, not purely exponentially, but scales like a squarton.
That specific scaling, why is that important?
Because that exact scaling is characteristic of a critical point in physics. It signals where microscopic freedoms, all those ways to sum integers, suddenly condense into a kind of macroscopic order, revealing these deep, unexpected patterns.
The unshaped clay taking form.
Beautifully put. Then, jump forward about a decade to the 1920s, Albert Einstein.
Okay.
He was working on the statistics of indistinguishable particles, bosons. He used partition functions that were mathematically very similar to Ramanujan's.
To describe how these particles distribute themselves into energy states,
Exactly. And this led him to predict Bose-Einstein condensation.
where particles collapse into the lowest energy state.
Below a critical temperature, yes, a huge fraction of them just drop into the ground state, acting like one coherent entity, like a superatom.
And the crucial point is,
The underlying mathematics describing Ramanujan's number partitions and Einstein's quantum gas condensation are essentially identical. It's the same mathematical structure describing order emerging from chaos.
okay, Ramanujan, Einstein.
Huh.
This is wild.
It appears to be the same fundamental mathematical structure governing how systems optimally distribute finite resources and undergo these critical phase transitions to create order. It seems universal. There's fascinating work by Tanaka and Kunin called Noether's learning dynamics. They show that even if your loss function has perfect symmetry,
The thing the AI tries to minimize.
right, the learning algorithm itself, like gradient descent, can subtly break that symmetry during training, leading to the emergence of almost conserved quantities, those Noether charges again, that pop up during the learning process. It helps explain why certain training methods work so well. They're implicitly finding these invariants during the phase transition.
That's clever. What else?
There's Noether's razor from van der Udera and colleagues. They show you can design models to explicitly discover conserved quantities from data by parameterizing symmetries.
So applying Noether's theorem in reverse. Find the symmetry to find the meaning.
Exactly. To improve generalization, find the invariant, understand the core concept.
Then you mentioned curvature earlier.
Yes, work by Gostolai and Arodinon on dynamic Olivia Ricci curvature identifies these curvature gaps in networks. These gaps mark boundaries between communities or bottlenecks, and they seem to correspond exactly to these phase boundaries, where variance crystallizes into structure, like the boundaries between ice crystals forming in water. It all seems to link up.
It really is an aha moment. Seeing math from 100 years ago predict cutting-edge AI behavior.
It makes you wonder how much deeper these connections go.
Okay, so if this profound phase transition happens in AI, what about us? What about the human brain?
That's the next logical step, isn't it? Can we apply this Bose-Einstein analogy for awareness itself?
How would that work? Information at different temperatures in the brain?
Kind of. Think about different levels of coherence. Below the critical point, maybe you have high entropy, lots of unstructured randomness.
Like dreams or hallucinations, disorganized thought.
Potentially. Information is there, but it lacks stable form, clear, conserved meaning. It's like a gas, particles everywhere.
Okay, then at criticality.
That's the proposed sweet spot. The system achieves system-wide order. Emergent properties arise stable consciousness, meaning as an invariant observable. Information is integrated, coherent, but still flexible.
And above the critical point. Too cold.
Too rigid, overcompressed, locked into fixed states. Think perhaps of coma or deep sedation. The system is frozen, unable to adapt or process novelty effectively.
Like a solid block of ice.
Too structured, no dynamics left.
And you mentioned this connects to existing theories of consciousness, like IIT.
Yes, integrated information theory. IIT's core idea is that consciousness emerges when information is both highly integrated, connected, and highly differentiated complex.
Finding that balance point again.
Exactly. Our condensation at criticality model suggests that IIT's main measure, phi-5, which tries to quantify consciousness by measuring that integration differentiation balance, is effectively a network coherence metric. It should be directly related to the network's spectral gap size and its eigenvalue structure. It's potentially the same physics of information described in a different mathematical language.
So IIT might be measuring proximity to this critical phase transition boundary.
That's a plausible interpretation, yes. And remember those Ramanujan graphs?
The optimal expanders.
There was a powerful recent proof, just this year, 2024, by Abdallah and colleagues. They showed rigorously that Ramanujan graphs are globally synchronizing,
Meaning
they inevitably converge to a state of complete coherent synchronization from almost any starting condition. They just naturally pull themselves into order.
wow. So if the brain evolves towards Ramanujan-like structures,
It might be naturally optimizing that variance bias trade-off, yes, but also inherently pushing itself towards a state capable of stable, coherent thought. It's like there's a built-in drive towards optimal processing and synchronization.
which leads to this really provocative idea.
That consciousness itself might only emerge right at this boundary, the Ramanujan-Einstein boundary.
The point of maximum information integration speed, maximum efficiency, without collapsing into rigidity or dissolving into chaos.
It's a novel hypothesis, but it synthesizes all these threads. The physics of condensation meets the geometry of information networks.
And this brings back the role of the PSC and hippocampus.
Absolutely. Their job in gauge switching, handling novelty, abstract rules, it fits perfectly. They are navigating that curved cognitive landscape, constantly working across different representations to extract the invariant meaning charges, especially when things are complex or ambiguous.
They're operating right at that critical edge.
It seems plausible they're heavily involved in computations near that edge. It even resonates with other theoretical models, like the projective consciousness model, PCM, from Rudroff and others.
What does that propose?
It formalizes subjective experience using 3D projective geometry, where changes in viewpoint are treated as gauge symmetries. It reinforces this idea that the brain might be implementing these internal geometries, these gauge theories, with consciousness emerging from maintaining invariance across transformations.
It really makes you ponder your own conscious experience right now. Is it operating at this delicate edge?
And could different states of consciousness focused, dreaming, meditative, correspond to slightly different phases or locations relative to that critical boundary in your neural parameter space?
Mind-bending stuff. What does this mean for understanding the speed of thought?
We've been using speed of thought somewhat metaphorically, but the claim here is more literal.
How?
That spectral gap bound, the sources propose, this is literally the maximum speed information can propagate through that network structure without losing coherence.
It's not just an analogy, a hard limit.
A fundamental physical limit for that information space. It dictates how fast patterns can truly emerge, how quickly signals can mix reliably, the speed limit at which meaning can actually crystallize from the chaos.
So understanding can only happen so fast based on the network structure.
That's the implication.
Okay. So for designing AI, the principle is clear then.
Build architectures that naturally live near this edge of condensation. Balance the exploration and coherence right from the start.
And potentially, you could even predict how well an AI might generalize just by looking at its structure.
That's the hope.
Imagine that. knowing if an architecture is promising just from its blueprint.
Architecture design itself, we could aim for specific spectral properties from the get-go, maybe use spectral initialization to set up the network connections favorably.
That feels much more fundamental.
It does, and the evidence suggests their condensed representations capture something more fundamental, more meaning-preserving. They're not just memorizing pixels, they're learning underlying concepts.
And you mentioned connections even beyond AI and neuroscience to basic physics.
Yeah, just briefly, there's related thinking in other areas. Ferrari and colleagues framing quantum thermodynamics as a gauge theory.
Where work, heat, entropy become gauge invariant, conserved quantities.
Exactly. It shows the power of symmetry and invariance across different physical domains. Or even Eric Verlinde ideas about entropic gravity.
Linking space-time geometry to information theory. Gravity as emergent.
Right. It further supports this deep theme that geometric concepts like curvature or bounds can be reinterpreted as fundamental constraints on information itself, perhaps even down to the fabric of reality.
It all seems incredibly interconnected.
It really does. The same deep principles seem to echo across scales and domains.
So we really hope you, the listener, can take this framework and maybe see things a bit differently.
Observe the world, maybe even observe your own thoughts. Okay, so last time we really got into this idea of the speed of thought
Right.
and that really profound concept that meaning itself, real understanding, it doesn't just pop up, it actually crystallizes.
You're at the very edge.
Exactly, the edge of how fast information can move through a system. It's like this critical point where raw data finally settles into something stable, true understanding. And today we're taking maybe a slightly unexpected path for guidance on getting that kind of clear perception.
Okay.
We're looking at Wallace Stevens' poem, The Snowman.
Ah, Stevens. Interesting choice. Not just poetry then.
Not just poetry, no. It feels like a surprising guide, actually, for how we approach information itself.
It really is. What's so fascinating, I think, is the poem's core idea. Its instruction, really. You need to cultivate a mind of winter.
A mind of winter. Okay.
Stevens means this quite seriously, I believe. It's not just some pretty metaphor. It's a call for a really detached, objective mindset. He writes, "One must have a mind of winter, to regard the frost and the boughs of the pine trees crusted with snow, and to really see those details like the junipers shagged with ice, or the spruces rough in the distant glitter." The poem says you need to have been cold a long time. It's about embodying that stillness, that chill, experiencing that prolonged cold so you actually notice the subtle stuff.
The things others might miss because they're just feeling cold and miserable.
Exactly. They're too busy projecting their own feelings, their own discomfort onto the scene. This is about getting past that.
So it's like stripping away our own subjective filter to truly see what's actually there. That sounds quite almost...
Precisely. Yeah, that's a good way to put it. This mind of winter, crucially, emphasizes shedding those emotional judgments.
Okay.
Like Stevens gives the example of the wind. You don't hear the wind and think misery, which, let's face it, many of us might on a bleak day.
Sure. Or, oh great, another Monday morning.
Instead, you just hear it as it is, the sound of the land full of the same wind that is blowing in the same bare place.
Just the wind.
Just the wind. It's the ultimate detachment, really. Seeing reality purely, without layering on our personal projections, our desires, our emotional noise.
I can really see the appeal of that, just observing without a commentary running in your head. But okay, let's connect this back to our deep dive. How does this mind of winter help us with our big theme? Perceiving the world without illusions, seeing that unvarnished landscape of reality, and maybe more practically, extracting invariant meaning from complex sources.
Ah, okay.
If I'm looking at a whole mess of conflicting information, say news reports or scientific papers, how does being a snowman help me find the actual truth, the thing that doesn't change?
It's directly analogous, isn't it? That kind of objective clarity, that stripping away of the emotional noise. That's exactly the process we need for extracting invariant meaning. When you cultivate this winter mindset, you're less likely to get bogged down by, say, the emotional language or the persuasive tricks in a source.
The spin.
Exactly. You're
Right.
looking past that. You're searching for the core facts, the patterns that persist, the truths that hold up, regardless of how the information is dressed up or framed. You're looking for what's invariant.
Okay, I see the connection.
And if we zoom out even further, this idea of detachment aligns perfectly with that scientific concept we've touched on. meaning as the knower charge of cognition.
Noether's theorem again. The symmetries in conserved quantities.
Precisely. Just like in physics, where symmetries lead to conserved quantities, the idea here is that fundamental meaning, the stuff that doesn't change, persists through cognitive transformations or compressions of information. It respects the underlying symmetries of intelligence.
And that's where information crystallizes, like we talked about with the speed of thought.
Exactly.
Yeah.
It's where things condense at that boundary, what we've been calling the Ramanujan-Einstein boundary, where all that complexity resolves into something elegant, stable, and crucially conserved. It's about finding that core signal in all the noise.
So bringing it back to you, the listener, think about this. How might cultivating your own mind of winter help you? Could it empower you to cut through the sheer volume of emotional noise and information overload we all face? Could it let you perceive the true conserved meaning that's often hiding right there in plain sight? Whether you're reading a dense report, listening to debate, or just looking out the window.
It's a powerful thought.
What if that stillness, that cool, objective observation Stevens writes about? What if that's the real key to seeing the true landscape of reality? Something to consider